Welcome to our video explanation for Lesson 9, which is polynomial inequalities. And the first thing we have to remember is what it means when we have an inequality that is similar to the last lesson we did, except that now we're dealing with a situation where we have a less than, greater than, less than or equal to, or greater than equal to sign. So the first thing we want to do is just make sure that we understand what this question is asking. So for now, don't worry about the steps, but we're just going to look at this example 1 and see what the question actually says. So we're trying to solve for when 4x to the power 4 plus 2x is greater than 9x squared minus 3. And because this is our example, I've included the diagram to the right of what the two functions look like if we were to graph them on top of one another. So we have in red 4x to the power 4 plus 2x, and in blue 9x squared minus 3. And we want to know when all of the places where the red graph is bigger or higher up than the blue graph. So if we had the graph, we could come up with an estimate of all the places where the red one is higher than the blue one, and the intersection points are where it's going to flip between the two. But even with the graph, it's not exactly completely straightforward as far as figuring out what those exact values are. So we're going to start going through this list at the top of what we're going to do. So the first thing is put all the terms on the left and leave 0 on the right. In order to do that, we want to just follow our general order of operations. So as though it was an equal sign, we can move everything around, but we remember that we're going to reverse the inequality if we multiply or divide by a negative. And since it's been a while, we're going to make a little note of that. So reverse the inequality when multiplying or dividing by negative. Hopefully you remember that from Unit 1. So in this situation, we won't have to multiply or divide anything by negative. We can simply move everything to the left-hand side. And we like to write all of the coefficients in order of descending degree. So we're going to keep that 4x to the power 4 at the beginning. And my advice is to move everything to the side that leaves the leading coefficient positive. So if this had ended up being negative 4, we probably would like to have it on the other side where it would be positive 4. So we've got something like this. The key at this point is to get 0 on one side, because now we can factor and figure out the places where it is equal to 0, which will help us figure out the places where it's greater than 0. So if we're following along at the top with our steps, we've now put all the terms on the left, leaving 0 on the right. Now we're going to find the roots of the polynomial. We know how to do that from previous lessons. It's going to involve factoring that left-hand side. So in order to factor, we're going to look at our possible factors, which are going to come from p over q, and in our case, p is 3 and q is 4. So we're going to start checking, and I like to do all of the work for this over here on the right-hand side, so we can keep our equation on the left all by itself. So we're going to start checking. And it turns out that p at 1 is equal to 0, so we're going to say that x minus 1 is our first factor. As always, when we get to this step, we're going to do synthetic division. The purpose of synthetic division was to factor this equation here on the left. So when we're done synthetic division, you always want to make sure that we come back and actually write in our next factor step. need to continue, so we're just going to keep going and keep attempting to find another factor. It turns out that if we keep checking, and I'm just going to write P2 so that we're clear that now I'm only talking about this part. So I'm just looking at factors of the new equation. So it turns out that once again, P2 at 1 is equal to 0. So that means that x minus 1 is a factor again. So I can just use my synthetic division with a 1 again. And again, we come back and actually write our equation. Over here. And if I was paying attention, I would have probably written x minus 1 squared there instead of writing x minus 1 twice. But it's okay writing it like that. It's still mathematically correct. I'll just remind myself for the next step that we can put those two together. Now we have a quadratic that we are going to attempt to factor using our strategy of man. Remember here, you can always use the quadratic formula. So if you're not sure if that will factor or not, you can use the quadratic formula, and if you get whole numbers, then you know that, oh, you could have used man, but that it will still work. It turns out in this case we can use man, and when we factor, we're going to get this. So right now, this is a very important step for us. This is our fully factored expression. And if the question had asked for when these two original functions were equal to one another, this would say equal 0 instead of greater than 0, and we would just have to read off the zeros. We would say when x equals 1, x equals negative 1/2, and x equals negative 3 over 2. But because it is greater than 0 right here, we're going to have an extra couple of steps. So our first step is the same as always. We're just going to state what the zeros are. 1, negative 1/2, and negative 3 over 2. We have two choices at this point. Usually we're going to use a sign table. You could also draw a graph. As long as you're careful about the end behaviors, the graph will help you out, and you can figure out whether or not we are above or below 0 on either side of those zeros. So you can use the graph, or you can use the sign table. I'm going to show you the sign table first, and then I will show you how to do it using the graph. Turns out that the sign tables will be revisited in further units, so it is a good skill to start getting used to doing. So when we set up a sign table, the way this is going to work, we're going to draw a table, and along the top we're going to put each section or each factor of our equation. So we're going to take the x minus 1 squared and give it its own section, and then 2x plus 1, give it its own section, and 2x plus 3. If there had been a constant in front of this equation, it would have gone right there. Let's say there was a negative 3. You're going to give it its own column in the table as well. So we separate all the factors, we write them down, and then we have to figure out all the different sections of our graph. So if we look at the zeros, we're going to put them in order from smallest to largest. And I'm just going to jot that list down. So we rearrange them so that we have them in order: negative 3 over 2, negative 1/2, and 1. And we want to separate our graph to the left of all of these zeros, in between each zero, and to the right of all of these zeros. So to the left is going to be the section that is less than negative 3 over 2. So you can write x is less than negative 3 over 2, or you can use our notation from the previous unit, where it said between negative infinity and negative 3 over 2. So that's the far left side of our graph. The next section is going to be between the negative 3 over 2 and and the -1/2. It's really important at this section that your zeros are in the right order. So if they weren't in order from smallest to biggest, your intervals will be all mixed up. And then our next section is between -1/2 and 1. And our final section is going to be to the right of 1. So from 1 to 3. And I want you to realize what we did here, that we just separated our graph into all the possible little vertical sections. So we have one vertical section from -infinity to -3/2, and then each section starts where the previous one left off. So we basically cover all the possible x values broken into sections. Now what we are going to do is fill in this table, but we're not going to put numbers. We're just going to put plus and minus signs. So I'm just going to write here for your note, all of these blue things were all the factors. And all of the black sections came from the zeros. So this is the part that you probably will need an explanation for. What you're going to do is pick a number that is in the first interval, so between -infinity and -3/2. You don't want to pick a decimal if you can avoid it, or a fraction if you can avoid it. So what we're saying is any number that is less than -3/2. So an easy number in your head to pick would be something like -5. And then you're going to, so as long as you pick a number that's in that interval, you're okay. You don't want to pick the endpoints, so you don't want to actually pick -3/2. You want to pick something that is less than -3/2. So we're going to pick -5. And then in your head, you're going to come across for each of these sections and see what happens if you plug -5 into each one. So the first equation will be -5 minus 1, which is -6 squared, which will give us a positive number. So these are ones you should be able to just do in your head. At this point, the equations are very simple and very small, so you should just be able to figure out, is my answer going to be positive or negative very quickly. 2 times negative, so now we're in the next column. 2 times -5 plus 1 is -10 plus 1, which gives us a negative. 2 times -5 plus 3 is, again, -10 plus 3, which gives us a negative. And we're going to continue doing that in the entire table. So the next thing we have to pick is a number between -3/2 and -1/2. That's a little bit tricky. -3/2 is -1/2. So between -1/2 and -1/2, the probable number that would be the easiest would be to choose -1. So we're going to say -1 minus 1 squared will be positive. 2 times -1 plus 1 will be negative. 2 times -1 plus 3 will be positive. Take your time doing this. The first couple of times it may seem overwhelming and confusing, but once you get the hang of it, you'll be able to do this very, very quickly. Then we're going to pick a number between -1/2 and 1. So if you're following along, we're in this row. The easiest spot to pick there would actually be 0, and that's allowed. So we're going to say 0 minus 1 squared will be positive. 2 times 0 plus 1 will be positive. 2 times 0 plus 3 will also be positive. Pick a number now in this row to the right of 1. So we're going to pick something like 2. 2 minus 1 is 1 squared, which will be positive. 2 times 2 plus 1 will be positive. 2 times 3 plus 3, 2 times 1 plus 3 will also be positive. So when you're choosing numbers in the intervals, it does not matter if you choose a different number than I chose, as long as it's in the interval. So you don't want to choose the endpoints of the interval. You don't want to actually choose 1 here. It has to be bigger than 1. If you chose 1.1 or 7 million, you should get the same sign table that I did. So it does not have to be that exact number. It just has to be from the interval. Once you have your full sign table, we've got all of our pluses and minuses put in there. Now we have to turn this into something that we can answer the question. So this last column we just refer to as the entire function at x. And all we want to know is, will it be positive or will it be negative? So we're going to look across the row. So we're looking at the first row. If you look across the row, you have a plus, a minus, and a plus. When you put those together, the two negatives will become positive, and our result will be positive. You can think of it if you multiply a positive, a negative, and a negative. What do you get? The next row, we have a positive, a negative, positive, negative, positive, which will give us a negative. 3 positives give us a positive, 3 positives give us a positive. What this tells us is for a given interval. So for example, the first interval right here, our entire function is always above 0. For this interval, our entire function is above 0. And for this last interval, our entire function is above 0. So we are going to come back and look at where we started, and we said that we want to know right here when the function is greater than 0. So we're going to pick those 3 intervals. So therefore, the answer is going to be all of the x's that are elements of each of these intervals. If the question had said less than 0, our answer would be the opposite. It would be this part, and we would say between -3/2 and -1/2. And that is how you figure out these inequalities. I did say I would quickly show you the graph. One other thing I will point out, if it said less than or greater than with an equal sign, you have to include the endpoints, which changes your bracket from circle to square. So if it was when you are greater than or equal to 0, you should use a square bracket there, and here, all of these places, and you would notice that the ones bump up to one another, so you can put that all in one interval. We will worry about that with the farther example. I did say I'd show you a quick graph of how you can figure this out with the graph. You draw your graph, you put in your zeros at 1, at -1.5, and at -0.5. And then you would draw yourself your results, which is going to be a quotient with a coefficient. Okay, apologize for the interruption. We're doing a quick graph of something that is a quartic with a positive leading coefficient. So we know from before that means that our end behavior is going to have to be up, 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 up. And we know the behavior at the zeros, that the 0 at x minus 1 is a double 0. So over here it's just going to touch and then turn around. And because we're just doing a quick sketch, we don't have to stress about how high up to come for the local maximum and how far down to go for the local minimum. So a quick sketch is okay. We just want to know when it's above or below 0. And we want to know all the places where this graph is greater than 0. So we can shade out all of the bottom and pick the intervals that actually fit, which is going to give us the exact same answer. So from this whole section here is going to be from -∞ to -3/2. This section here is going to be from -1/2 to 1. And this section here is going to be everything that's bigger than 1. Notice that 1 is not included in any of our intervals. It's the end, and we use a circle bracket, meaning that at the actual zeros, our function is not greater than 0, so we don't include that. And that was the explanation of how to do a polynomial inequality.